Okay, hello and welcome to these end of chapter review questions. Looking at Phys 1, Forces and Motion. And we start off by looking at this little set of questions here, then we'll go on to the next one, and this is all going to be to do with forces and motion. Then we'll go on to the final set over here. Alright, so this is the kind of thing that we're going to do. We're not going to do some of the kind of plot graph ones, but some of the other calculations and so on I'll try and demonstrate using this little calculator over here, the ClassWiz, and I'll draw and handwrite some solutions onto the screen as well. Okay, so you start off with this one over here. This is essentially question 1. It says calculate speed in meters per second. Now this is where you're going to remember that your average velocity or average speed is given as displacement over time. Now I know in here it's looking at speed, which is a scalar rather than a vector quantity, which is our velocity, and that there is, remember, that's displacement generally within that equation there. So that one there is velocity, but we'll still stick with that equation. That's the one that IGCSE want you to essentially go and use, so we'll stick with that for now. So essentially if we use that, we know that we've got 100 meters and we know we've got 12.5 seconds. Essentially our S value is 100 meters, and our t value is 12.5 seconds. And it's a pretty good idea to go and actually write down your data on the side with units as well. So then all you're doing is actually just plugging your equations in. So now stick with that notation of b, even though it's that scalar speed. We just put in 100 divided by 12.5. Don't need to worry about anything else because it's already in meters and seconds. Okay, meters and seconds. And just bring up the calculator over here, so 100 divided by 12.5, and there you go, that's your answer, is 8 meters per second. So that's that one done. Then we've got here a bit of info. So we're told, number that, number 1, okay, number 2. So we're told here that we have a speed of 350 meters per second. And when I'm being asked how far, so what do we know? Equations with how far suggests some sort of distance or displacement. So that's what we want to kind of know about. Let's look at what we've got here. We've got time. Okay, so what kind of equations do we know that have v, s, and t? Here we go. v, s, and t. That is our v equals s over t. Now, if you want to, you can think of this as a triangle, really small triangle. Let's replace that. Yeah, looks a little bit nicer, a bit too big. And we've got essentially v is s divided by t. So if you want to know what is this one here, the distance or the how far or the displacement, then really what you're going to do is s equals v times t. Alright, so for 2a, I should probably actually do that over here. Okay, 2a. So 2a is 30 seconds, and we're using s equals v times t. We know that our v is 350 meters per second, and our time is in seconds, so no worries about trying to do any conversions there. Pretty nice and straightforward. If you want to do 30 seconds, so 350 times 30, let's bring the calculator again. 350 times by 30, 10,500 meters. Why is it meters? Because we did meters per second times by seconds. Okay, so 2b. This time, look at what we've got. We haven't got seconds, we've got minutes. Almost cross out the question there, we go, got minutes. So what we want to do this time is 5 minutes into seconds. What are we going to do? We're going to essentially do times by 60. So if we do that, then we've got 5 times 60 here. Why do we do that? Because each minute has 60 seconds. 5 minutes must have 5 lots of 60 seconds, which is 300 seconds. Now we use our equation, s equals v times by t. V is still the same as before, it's still the same jet, 350 meters per second, times by the time, which is 300 seconds. And lo and behold, we're going to get 350 times by 300, 105,000. Okay, 105,000 meters. Again, why is it meters? Meters per second times by seconds, so there's seconds cancelled out, we're left with meters, and that essentially is the answer for 2b. That's 2a. This one here we might as well do 2c. I'll stick with the red for now. This time look, we've got half an hour. Okay, so how do we go from hours into minutes? Because really we want to be in seconds. So that there is going to be times by 60, and that there is going to be times by 60. Again, we're starting off with half an hour, or 0.5. 0.5 times by 60 gives us minutes, times by 60 again gives us seconds, and that means that we actually end up with 0.5, not divide, times by 60, times by 60, or 1,800 seconds. Going using S equals V times T, our V is still 350 meters per second, times by 1,800 seconds, and we end up with 350 times 1,800, 630,000, 630,000 meters. And there we go, that's our answer to 2C. Now what I'm going to do is I'll do number 3 on the left hand side of the screen over here, but I'll do it in different colour just so it doesn't get too confusing. Okay, so let's do this one over here. So number 3, in blue. This time have a look at what we've got. So we're just going to write down some of our data. So our speed there is 0.0004, yeah, 0.0004 meters per second. How long will it take? How long will something take? That suggests the time. We don't know. But what we do know is that we're looking to try and go 1.6 meters, meaning that our S, or our displacement, or our distance there, 1.6 meters. Note that we don't actually need to do any conversions, regardless of that number looking really, really weird. It's just walking or moving at a snail's pace. Get it? There we go, snail crawling. Yeah. Okay, so what we want to do here is again just use our equation. This time we want to do it so that time is the subject. So time equals our S value over our V value. So it's punching the numbers. 1.6 meters divided by 0.0004 meters per second. Let's go and do that calculation. 1.6 divided by 0.0004, and we get 4,000 as our answer. 4,000, and remember we've been working out time, so that is 4,000 seconds. All of our units were standard units, and there you go. That is essentially that slide over. So feel free to, in fact, feel free to kind of pause the video, review these, and then continue with the next part. We're going to look at another series of questions. Okay, so here number 4, we have identify in which graph the object is doing various things. Moving backwards, moving slowly, moving quickly, not moving at all. Now the distance time graph, one thing to sort of watch out for is this. I'm not going to be doing 5, 6. In fact, I won't do 6. That's a plot graph, so I'm just going to cross that out. Not what I'm going to do. I will do the sketch graph. I'm going to try and do some of the others there as well. Again, I can see sort of sketchograph questions, which is fine. Okay, so with number 4, in which graph the object is moving backwards? And that would be this one over here. How do we know that? Because the distance, on distance time graph, if the graph is going back towards the x-axis, remember that is your x-axis, the time axis, then it shows that it's moving in the opposite direction to what it initially was, meaning in this case that it's going back towards the start. We can assume that going back to the start would be backwards. Moving slowly, so it is moving, but it's moving slowly. Well, that's all to do with the gradient. So if the gradient, let's just do this actually. The gradient of a distance time dt graph equals speed. The steeper it is, the faster the motion. Okay, the steeper the graph, the steeper the line, the greater the speed. Alright, so Moving slowly is going to be this one over here. How do we know that? Because it's less steep, it's shallower than this one over here, meaning that one must be moving quickly, which is our C. And not moving at all means that it stays at the same distance all the time. Look at this one here, flat line. That means that it got to this distance, it stayed at that distance for this period of time. That one must not be moving anywhere, it is stationary. Number 5, sketch. Okay, sketch graph. Sketch a distance time graph to show the motion of a person walking quickly, stopping for a moment, then continuing to walk slowly in the same direction. Here we're just really going to put together all these different things. Remember, C was moving quickly, D was stopping or not moving at all or being stationary, and C over here was, did I do that right? Did I say A, B, C, or did I use blue letters? Not sure. But you know the idea, that's quick, that's moving quickly, that's stationary, and that's moving less quickly, because it's shallower. So if I was going to go and sketch graph, and it is just a sketch graph, so don't worry too much here about trying to fill in numbers, it's really the shape that the examiner is looking for over here. So I'm just going to put D for distance, T for time. No, in fact I won't do that because that is not the notation we've otherwise been using. So distance there, and time there, although we do refer to it as dt graph anyway, so I guess I could have left it at that. The reason why I didn't though is because we're using the equation v equals s over t, where that is our displacement, that is our velocity, and that is our time, as we did on previous questions. So what I'm going to do here is a bit of a steeper gradient. That's to show the moving quickly part. I'm going to just label that part 1. We've then got the stationary part, which is, says here, stopping for a moment, so we should probably keep that pretty short, and continuing to walk slowly but in the same direction. So we're not going to go back on ourselves, that would show that we're going back towards the start. We're going in the same direction, but not at quite a high speed as before, and therefore what I've just done there is a shallower gradient. So that was part 2, that was part 3. Notice how this is a lot steeper, number 1 is a lot steeper than part number 3. I said I won't do 6, it's a plotter graph. You can practice doing that on some graph paper should you wish to. The only things to watch out for when you do plot a graph is to make sure that your scale is going up in a set value or set number. In this case, I would probably have a look at your graph paper. I'd probably go, in terms of distance, I'd probably go up in 2s. So if this was my number 6, imagine this is on graph paper. I'd start off here, have a 0. Remember, this is your distance, this is your time. That would probably be 2, 4, 6, 8, 10, should be even. And what do we have for time here? It's definitely going up in 0.05, so that makes our life pretty easy. 0, 0.05, 0.10, and you get the idea as we go along. That'll be 0.15 and so on. Okay, that's all I'm going to do there for 6. The diagram shows below a trail of oil drips made by a car that travels along the road. The oil is dripping from the car at a steady rate of 1 drip every 2.5 seconds. Describe the way the car is moving. Well, it looks like here, and you might want to disagree. If you do disagree, put it into the comments. But that looks to me as if that is about the same distance apart every single time. It's just to the left of that white line below. Okay, it looks about the same distance apart. Maybe it's not. Maybe that's not quite the best way to go and judge it. I don't know how accurate this diagram is. Let me just cross out the blue lines. I still reckon that's about equal in terms of distance between them. As I say, if you do disagree, feel free to put that into the comments. So I would say here that 7A, that is 7A to me shows that the car is moving at a constant speed. Now by all means you could say a constant velocity, that would be fine as well. Okay, just leave it as a slash, there we go. Either of those is fine. The distance between the first and the 7th drip is 135 meters. Determine the average speed of the car. Okay, so what this is saying here, let's imagine, it doesn't really matter, but let's imagine this is going from left to right. So that is 1, 2, 3, 4, 5, 6, 7. And that suggests to us that if this was kind of 0 time, that's 2.5 seconds later, that's 5 seconds later, 7.5 seconds later, 10, 12.5, 15 seconds later. Okay, so we would say there we start off as kind of time equals 0, that's our 0 time. That's then 2.5. How do I know all this? Because it tells us here the oil is dripping at 1 drip every 2.5 seconds. That's then another 2.5, another 2.5, another 2.5. So that would be 5 seconds, that would be 7.5 seconds, and so on, all the way to 15 seconds. Lo and behold, when we look at 7b, what kind of information do we have? Well, we're looking for determine the average speed of the car, and we're going to use v equals s over t. Check back on the previous slide if you're not too sure about that equation. So using this, we know that the distance there is 135 meters. We know that the time, by doing this little calculation where our 0 time is the first drop, we've worked up all the way to 15 seconds, so that's all happened over 15 seconds. So our v equals s over t is really 135 meters divided by 15 seconds. And if we do that calculation, I'll show you here, 135 divided by 15 gives you 9, and you're going to think, what are the units? Meters per second. Everything is in standard units, so meters per second. Okay, so that is that one. I'm just going to change colour over here. In fact, I won't yet. I'll do it when we get to a little bit more kind of cramped areas. Okay, so 8A, here we go, 8A. It says here a car is travelling at 20 meters per second. It accelerates uniformly at 3 meters per second squared for 5 seconds. Sketch a velocity time graph for the car during the period that it is accelerating. Include numerical detail on your axes of your graph. So this time it specifies it's not just after the shape like it was in number 5. We have got to give a little bit of information here as well. And this is pretty interesting because whilst we can kind of start off and we can go, okay, so here is my velocity time graph. I'm just going to put v and t. This time v does mean velocity. And we've got here kind of starting off at perhaps 0, 0, but I won't do that. I'll just kind of put 0 there, 0v, 0t. And we know that the car is travelling at 20 meters per second. Now we don't have to do a scale because it is a sketch graph, but it does want numerical details in there. So let's say that this is your kind of 20. We'll put there some units, meters per second, and then it's going to be in seconds there. And it's travelling along at 20 meters per second. It tells us that it's travelling along at 20 meters per second. But it only wants us to do a graph during the period that it is doing what? Accelerating. So that means we really need to know, we really need to know and understand that if it's accelerating, graph is going to go up. But by how much? How much does the graph actually go up? Well, in order to do that, we need to know what the final velocity is after accelerating. Now this is where we go back to acceleration is final velocity minus the initial velocity divided by the time taken. And if you rearrange this equation, what you want to do, with a bit of algebra here, you want to times by t on both sides, so you end up with at equals v minus u, and you know that you've got t below, t above, that cancels out. And then what you want to do is, on both sides, you want to add u. U is the initial, that's our initial velocity. V is the final velocity. And remember, there's no reason for this other than v is velocity and u in the alphabet comes before v, so it makes sense that we put that as the initial velocity. So if you add u to both sides, you then end up with u plus at equals v. I prefer writing the other way around, so v is u plus at. Well, in this case, have a look at the info that we've been given. We've been given the acceleration, which is 3 meters per second squared. We've been given the time, which is 5 seconds. We know the initial velocity is 20. So v equals u plus at actually becomes, let me do it on a different line, that would actually become, that'd be here, 20 meters per second plus 3 meters per second squared. The only reason I've done this in brackets is so that we know which bits to do first, and we'll then do that times by time, which is 5 seconds. I have to put the units in, but I'll do it for completeness anyway. And what we're going to do, just going to do this on my calculator. 3 times 5, I'll do the AT bit first, and then add on my 20 meters per second, the initial velocity, and I get over there 35 meters per second. So I know that this is going to end up at 35 meters per second. So I have a graph that looks like that, and we can assume it to be, well, we've taken it as a constant velocity. And how long did that take? Well, we started off at 0 time, we've ended up at 5 seconds. It tells us here that this happened over 5 seconds. Calculate the distance the car travels while it is accelerating. Well, you've got 2 ways to go and do this, and it really doesn't matter which way you go and do this. You could do it graphically, so you can actually go and use this graph, and I'll show you both ways to do this. So let me just change the pen color here. I'll kind of show you this using the graph method. So what we want to do is just work out what is the area under the line. Essentially the area, say under the line, the area between your graph and the x-axis on a velocity time graph gives you the distance. So that there is the distance or displacement of your vehicle or object or whatever it might be. So how do we go and calculate that? Well, I'm just going to cut this up into 2 shapes. And the first thing I'll do is just work out the area of this shape. I might just call that shape A. A makes a rectangle, so I'm going to say that A is 20 times by 5. That's the area of it. That's 100 meters. Okay, we're working in meters per second, and seconds, so that's going to be in meters. This I'm going to call B. Okay, so I'm going to call B, shaded in a different colour. And B makes a triangle. But the height of this triangle from there to there is actually 15. It's 35 minus 20. The base of it is 5. So we do half times base times height. Well, in this case, that's half times 5 times by 15. And we end up with, as essentially our answer here, we will get 5 times 15. Just do divided by 2. I could do it times by half, it doesn't matter. And you get an answer which is going to give you 37.5 meters. So we go 37.5 meters. Okay, explain the difference between the following terms: average speed and instantaneous speed. So let me just put in again. In fact, I'll stick to, no, let's go with a different colour. Go with this kind of maroon colour there. So 9A, we're looking at the average speed versus instantaneous speed. Average speed is the total distance travelled for a journey divided by the total time taken. Okay, and I kind of regret trying to do 9A over here, because what I want to go and say is, if I just star that off, I'll put it over here. I won't use that colour for anything else, so it should stand out. Instantaneous speed is the speed at a specific or particular time, essentially at that instance or at that moment in time. Okay, so average speed, you look at what is the overall journey. When you think about your average speed to school in the car, there'll be points where you stop, points where you are driving very fast on the highway, points where you're driving pretty slowly, but essentially your average speed just takes into account what was your total distance to school divided by the total time taken. The instantaneous speed is the instantaneous speed, speed at a particular instant or moment, and that means that when you are stopped, you'd say your instantaneous speed is 0. When you're travelling very quickly on the highway, you might say it's 70 miles an hour, and so on. Differences between speed and velocity. Put that one up here. So let's go again, different colour, with the tail leaves back from there to kind of correspond with each other. So here we go with 9b over here. Speed is the distance travelled per unit time, size, but no direction. In other words, we would say speed, this is a bit more info than you actually need to answer that question, but we might as well put it in. Speed is a scalar quantity. On the other hand, when we think about velocity, this is your speed, so it's your distance travelled per unit time in a given or particular direction. In other words, size and direction. Velocity is a vector quantity. Okay, so that's that number 9b done. 10 here says calculate the acceleration of the car. It accelerates uniformly meaning at a constant rate. Rest to 24 meters per second in 6 seconds. Let's just jot down our kind of key data here. This is 10. So we're told that there is a constant acceleration. We're told it's starting from rest, so our initial velocity is 0 meters per second. We're told that the final velocity is 24 meters per second, that's what it gets to. We're told the time is 6 seconds. We're trying to find the acceleration. Well, this is kind of useful. We're looking at this equation again, this one here. So acceleration is v minus u, okay, change in velocity, final velocity minus initial velocity divided by the time taken. And so that in this case is going to be our 24. Take away 0 divided by 6, or 24 divided by 6 is going to give us 4 meters per second squared. We don't have to really worry about doing minus 0. We can do it, but it will give us 24 anyway. 4 meters per second squared is the answer there. Finally, we've got a little bit here to do with sketch graphs, 11a, 11b, 11c. I'll try and do this one in a different colour as well, actually. Go with a green, you haven't had any green on here. Go with a little bit of green. Okay, so 11a, there we go, 11a. Moving with a constant velocity, so this is velocity time graph. Be careful with your wording there. Okay, don't end up doing a distance time graph, it says velocity. Velocity of 6 meters per second, constant velocity of 6 meters per second. I'm going to sketch graph, I'll put some numbers in as well. That's essentially going to be our 6 meters per second. There we go, straight line. You might think, oh no, why is that a straight line? When that was a straight line, and that meant stationary. That's distance. That is a distance time graph. This is a velocity time graph, okay? Velocity time graph, VT. So that tells us that it travels 6 meters per second all the way. That's why it's a straight line. Okay, not the same as a straight line. Distance time, well, that would mean that it's covering no distance, and it would be stationary. This is not stationary, it is moving at 6 meters per second. B, here, accelerating uniformly, the constant acceleration, from rest at 2 meters per second squared for 10 seconds. Calculation is required. Okay, so this time we're going to be using this version, the V equals U plus AT. So what we want to do here is essentially start off with from rest is 0. We're going to put V, we're going to put T, VT graph, and it's going to take 10 seconds. Okay, so we're going to put 10 now. So 0, put units in, put a second in. And what are we going to do? We're going to use our V equals U plus AT. In this case, that's 0 is our initial velocity, plus acceleration, which is 2 meters per second squared, times by 10 seconds, so that is 20. That means this goes up to 20 in 10 seconds. Now I've done my calculation there, which again I kind of regret, but hey, I'll just kind of put this up over here, just about reaching 10, kind of. I'll just put in that is 20 meters per second. There we go. I've got some values in there. If only I could show you the units. Oh dear, that was bad. bring that back. Pretend that never happened. There we go. And we just put in there that is 20 meters per second. There we go, all done with 11b. And finally 11c. 11c, we'll look at this one, a little bit different. 11c says decelerating to rest. Decelerating to rest. So that means that in this one, we're actually looking for something a little bit different. This time we're actually looking for u. So what I'm going to do is subtract at from both sides. So if I say I'm happy with this equation, v equals u plus at, and make sure that you are happy with these equations, because you'll definitely need them. That is going to be u, that's our equation there. And I'm just going to subtract at from both sides. That leaves me with v minus at equals u. Okay, v minus at equals u. So what am I going to do this time? Well, we want to know what was our initial velocity, because we have the final velocity that's given to us. It's at rest. We know the acceleration is 4 meters per second squared. The time taken is 5 seconds. So what we want to do here, essentially do v minus u, v minus u, v minus at, v minus at, v minus at equals u. So we want to go with 0, that's our final velocity. Take away our acceleration times time, that's our 4 times 5. Now remember, this is decelerating, so we can actually put in a minus 4. Minus 4 times 5 is minus 20. 0 minus 20 gives you 20. So what's going to happen this time is, this is our graph, this is our v over there, this is our t, that's our v, velocity, time graph. We know that it takes 5 seconds, so we can put here 5 seconds. And we also know that it starts off now at 20 meters per second. That was our u value. I might say that is 20 meters per second. And it ends up at rest. Just missed the mark slightly. And that's going to happen from 0. That one was 0 as well. And there you go. That set questions done as well. So yeah, really well done. And say message me, or feel free to contact me if you have any questions, or write comments, and I'll get back to you.